in this talk, I'll be talking about my work over the last 5 years in Bikram's group at University of Michigan. So this work started with my, actually earlier with Fanny Motamari in his PhD from 2013, where the development of applying finite element method discretization to solving the Kohn-Sham equations in a very systematically convergent and large scale manner started. And then I came in like 5-6 years back into this area. And so I'll be talking about the methodology of large scale Kohn-Sham calculations using finite element discretization, which led to the development of the DFT-FE code. And I'll be discussing some of the recent work we have done on developing an advanced preconditioning technique for accelerating the SCF in large scale and heterogeneous material systems. And then I'll be discussing an interesting application of systematically convergent and large scale DFT to study the dislocation core energetics in magnesium and magnesium alloys, and what are its implications towards ductility enhancement. So essentially, I'll be going from Ab-initio to kind of mesoscale the connection. And so the first slide I want to start off with, what is the need for large scale DFT calculations? So this is important in various material science domains. For example, surface chemistry of large nanoparticles, large biological systems, dislocation core structure and energetics, as well as other applications discussed in this workshop and the previous one, like grain boundaries, large Moiré supercells, like whose computation of the band structure requires very large number of atoms. So doing large scale DFT calculations at systematically convergent accuracy. So when I say systematically convergent, I'm talking about the discretization error. So we need a complete basis for that. It is very important to study these applications in a predictive manner. And one of the applications which I'll be focusing on in this talk is the technological challenge of low ductility in magnesium. So magnesium is the lightest structural metal on Earth, but so far it has not found use in aerospace and automotive sectors. We're still relying on steel and aluminum. The main reason for that is the low ductility of magnesium, and that is because in magnesium, the basal plane, it is very easy to glide, but the non-basal slip has a very high critical resolve shear stress, almost like 2 orders of magnitude higher than the basal slip. So we cannot get plasticity in the non-basal directions, which are like, so we can get through prismatic and pyramidal planes, but prismatic has a very high critical resolve shear stress, whereas the pyramidal planes, the stability and it can easily glide, but essentially the dislocations are metastable on the pyramidal planes, and that has been an issue. Like in terms of a mechanistic viewpoint, people have looked at how do we activate the pyramidal slip planes, and what recently has been found that there is a mechanism which tunes the small core energy difference of the screw dislocation on the pyramidal 2 and the 1 planes through dilute solute alloying of rare earths, and recently they have also tried other solutes. And by tuning the small core energy difference, they can significantly enhance the plasticity, as you can see in this tensile stress experiment. By just putting 1 weight percent of yttrium, we can get large plastic strains. However, in this, to make a predictive model from a computational standpoint, this small core energy difference and how it gets tuned by the solutes has remained an open problem, like how to compute it accurately. And as I'll be demonstrating later in this talk, this requires very accurate in terms of discretization and large scale DFT calculations reaching 6,000 atoms or 60,000 electrons to get the cell size convergence in the relevant quantities. So I will get back to this application problem, but let me first discuss the methodology of the finite element discretization applied to Kohn-Sham density functional theory. So Vikram in his first tutorial at IPAM and also the first workshop has gone over the theory of density functional theory and Kohn-Sham DFT. So I will go over this briefly. For a system with n electrons, we are actually solving this nonlinear eigenvalue problem, where which is a mean field approximation, where the effective potential is a function of the electron density rho, and the effective potential consists of the Vxc, which is the exchange correlation potential, which contains all the many-body quantum mechanical effects, and the V electrostatic is all the classical electrostatic interaction effects. And we're solving for the lowest n eigenstates, which are the psi I, the eigenfunctions, and epsilon I are the eigenvalues. And we have to solve this in a self-consistent manner because because the density is also dependent on the wave functions. And here the Fi's are the occupations which are given by the Fermi direct distribution, because in metallic systems, to avoid charge lossing effects, we have to smear them out. And also there is a constraint on the occupancies that it has to integrate to the total number of electrons. So what are the main challenges here? The main challenge is that this is a cubic scaling cost. And second, the widely used basis sets to solve this are primarily the plane wave basis, which have a large communication cost because they're global in nature. Hence, the routine applications of Kohn-Sham DFT have been limited to few hundred atoms. So our strategy has been to develop an approach using real space discretization, using which you can attain massive parallel scalability and be able to solve generic material systems very accurately and efficiently. So let's give a lay of the land of what are the widely used basis sets. As everybody knows, plane wave bases are very widely used, and for a good reason. They provide spectral convergence, so they're very efficient. And but however, they are restricted to periodic domains and periodic boundary conditions, and they provide limited parallel scalability, as I mentioned. The other commonly used basis set is the LCO basis, which is atomic orbital basis, which is in real space. But the problem with this is that it is not a complete basis, so systematic convergence is not guaranteed in this basis. Hence, there has been an increasing thrust in developing systematically convergent and scalable real space basis like finite difference, finite elements, p-sinks, wavelets. Among these real space basis sets, finite element basis is very attractive because it similar to plane wave basis, it is a complete basis. It provides systematic convergence, but unlike plane wave basis, we can adaptively refine the finite element. So it provides adaptive. Here's an example of so it's a piecewise polynomial basis, the finite element basis. So this looks like a third order finite element polynomial. So this is a C0 basis. So because we can vary the element spacing as well as the order of the finite elements, we can attain the systematic convergence using that. And because it's due to the adaptive refinement, we can solve both pseudopotential as well as all electron DFT problems. And further, the finite element basis allows for complex geometries and periodic, semi-periodic, and non-periodic boundary conditions. And because it's strictly local, the piecewise polynomials, it provides the opportunity for excellent parallel scalability. However, finite element bases have not been traditionally.
I was wondering, does it make sense to try C1 elements or, I don't know, even spline-based instead of C0 elements? So you're using C0 here, right?
Yeah, we are using C0, yeah.
Would it be worth trying C1?
Yes, but the C1 will be more smoother, but using C1 basis, one cannot solve the all-electron problem because you have a cusp in the wave functions at the nuclei. So to have a generic framework, we stuck to C0 basis. Yes. Yes.
What sense is your count also for that?
But if you have in metallic systems, the convergence is typically not guaranteed. Yeah, and also the atomic orbital basis, if you keep taking more and more atomic orbitals, it can get highly ill-conditioned. Yeah, so practically, practically it will be difficult to attain the completeness.
It's not a theoretical lack of completeness, it's a practical. Maybe is that? Or am I missing something?
Yeah, it's a practical.
Practical, yeah. So so coming back to why finite element bases were not very popular is because initially people tried linear finite elements and they found that you require millions of degrees of freedom per atom to attain chemical accuracy, whereas plane wave basis just requires a few hundred. So one of the initial work was how about we try higher order finite elements, and here I demonstrate two benchmark systems, a cubic nanoparticle and a periodic systems. And first we study the convergence of what is the degrees of freedom required to attain a certain chemical accuracy, which is 0.1 millihartry per atom, and with the increase in the finite element order. And we see that remarkable, we obtain a 3000x reduction in the degrees of freedom at fourth order finite elements to achieve chemical accuracy compared to first order finite elements. But the increase in finite element order increases the bandwidth of the Hamiltonian. So the cost per degree of freedom increases. So it is also important to see what is the CPU time in hours for higher order finite elements compared to linear finite elements. So here also we see that there is a 1000x computational advantage in using higher order finite elements compared to the linear finite elements. So the next challenge was that when we discretize the Kohn-Sham problem in the finite element basis, we end up with a generalized eigenvalue problem where H is the discrete finite element Hamiltonian and M is the finite element mass matrix, and this is arising because the finite element basis is not orthogonal. But solving a generalized eigenvalue problem is computationally costly. Hence, we recast into a standard eigenvalue problem using the square root of the mass matrix, because the mass matrix is positive definite. It has a unique square root, and we can do this Laudin orthogonalized Laudin transformation, which gives us a standard eigenvalue problem, which is the H using the H tilde, which is the transformed Hamiltonian matrix in the Laudin orthogonalized basis. But the construction of the mass matrix.
Sorry, I have a question about this here. So m to the minus a half, depending on how you define it, is a full matrix.
Yes, and that's what I was gonna. So it is also computationally costly to compute the m to the power minus half, because it's a sparse matrix still.
No, depending on how you define it, it is a full matrix or it's a.
Yeah, the sparsity can increase.
Not that sparse matrix.
Yeah, it's not that sparse. I mean, m is sparse, but once you take the square root and take the inverse square root, yeah, the sparsity.
Which square root are you taking?
So we're actually not dealing with a.
Oh, you don't. Okay, then I'll let you go.
Yeah, so that's so actually computing this m and dealing with the m matrix can be very costly. So what we do instead is that we use spectral FE basis, where the nodal points are the roots of the derivatives of Legendre polynomials, and in conjunction we use the Gauss-Lobato Legendre quadrature, which is coincident with the spectral FE nodes. So then it makes the mass matrix diagonal, and then the transformation is trivial. And just to remark this, the GLL quadrature introduces small error, so which is controllable. So we only apply this GLL quadrature to compute the mass matrix, but the Hamiltonian matrix is still computed using the usual Gauss quadrature rules.
Sambit, let me ask you like a complete structural engineer's question, right? You know about mass lumping.
Yes.
So mass lumping works out very. So what's the deal? Would that really mess things up?
No, actually, it should work. In practice, mass lumping should work. Yeah. That in fact, one of our collaborative funny is thinking in that direction. Yeah, that's. Yeah. So now we have a standard eigenvalue problem, which allows us to avail efficient solution strategies. And one very efficient solution strategy is the Chebyshev acceleration strategy. And why this is it's nice strategy is that when you look at the Kohn-Sham Hamiltonian, it's a very large discrete Hamiltonian. In fact, some of the largest problems we have gone have 100 million degrees of freedom, whereas we are only interested in the lowest occupied eigenstates, which maximum will be like orders of 100,000, even in the largest problem. So looking at less than, yeah.
I'm so sorry, but I'm going to get stuck on that if I don't ask the question. So how much more expensive is a generalized eigenvalue problem? Because the solvers exist, they're very robust, it's not a problem to use on the scale that I would use it. How much more expensive are they, and why are you worried about the generalized eigenvalue problem? It's great that you can fix it, but nevertheless.
So the generalized eigenvalue problem will, the solution strategies available there, one has to then solve them by eigenpair. Like for example, in the standard eigenvalue problems, one can use this filtering strategies more efficiently.
You can do the filtering.
Yeah, one can use.
You can doing sort of standard eigenvalue solves.
Like Krylov-Tour.
Specific things you're trying to do.
Yeah, specific things which requires us to have a standard eigenvalue problem. That's the reason. And because it's I think more tied to the nature of the Kohn-Sham eigenvalue problem, because we're only interested in the lowest occupied eigenstates compared to we are not interested in the full spectrum, all the eigenstates. So we have a very large eigenspectrum, and we're just interested in the lower part of that. So the Chebyshev acceleration strategy, instead of computing eigenpair by eigenpair, it approximates this occupied eigen subspace adaptively as the SCF progresses. So the idea is that we take this Hamiltonian, that is, and scale and shift it such that the unwanted spectrum lies between -1 to 1 and the wanted spectrum lies to the left of -1. Then we construct a Chebyshev filtering, which is a recursive filter, and it acts on a like a trial subspace. And the nature of the filter is that between -1 to 1, it suppresses the eigen spectrum, and to the left of -1, it drastically magnifies it. So when we apply this filter, and we get a subspace which is enriched in the occupied eigen subspace, and then we project the eigenvalue problem into the smaller subspace and solve a Rayleigh-Ridge step. So putting this all together, the algorithm of DFT-FE is follows. We start with the initial guess of the electron density, compute a discrete Hamiltonian for that electron density, perform the Chebyshev filtering, which gives us that subspace which is enriched in the occupied eigen subspace. We orthonormize the basis, the vectors in that eigen subspace, approximate eigen subspace, and then we project our Hamiltonian into the smaller subspace and basically do a Rayleigh-Ridge procedure. And finally, we compute the output electron density. And since it's a fixed point iteration, we apply mixing strategies, and I'll be also talking about a novel preconditioning method, which is actually very important for large-scale problems. So then we do this SCF until we go to convergence. So in this talk, I'll be not going into the computational architecture of DFT-FE, but I'll be happy to discuss this offline. I mean, some of these architecture aspects was also discussed in Vikram's talk in the workshop 1. So now I saw some benchmarks against widely used plane wave code, which is quantum espresso. I take a BCC monovacancy system, which is a periodic system, and with a ONCB pseudopotential, and we are solving both quantum espresso and DFT-FE to same accuracy, which is 0.1 millihartz per atom in both energy and 0.1 millihartz per Bohr in maximum ionic force error. And we see that and we compare the time per SCF in node hours as we increase the system size. And we see that as we increase the system size, the DFT-FE is more and more efficient, up to like a, yes.
For the uninitiated, what is quantum espresso?
Yes, quantum espresso is a very popular plane wave discretization based DFT code. It is also open source, and that's why we compare against it. And we are picking periodic system because plane wave basis is known to be very efficient for periodic system. So even for a such a system which is very nice for plane wave basis, we are able to outperform it by orders of magnitude. And the crossover point for a very small system, also we are able to like comparable. I mean, not very, very fast. But if you go to a non-periodic system where the plane wave basis, because it's a uniform basis, it doesn't have spatial adaptivity. So in the vacuum region, it cannot coarse grain. Whereas in finite element, because spatial adaptivity you can coarse grain, the crossover happens at a much smaller size. Even at 300 atoms, you're already like 3 to 4x faster, and like 500 atoms are an order of magnitude faster. And this is a recent work we have done on GPU porting DFT-FE to AMD GPUs, and also we have also ported to permuter GPUs. And so an example of a very large system, 2,000 atoms, 40,000 electrons, and we're showing the strong scaling going from around 60 to 100 nodes to 500 to 1,000 nodes. Like, and we're getting 60% parallel scaling on both front-end and permuter at 5x relative speed up, and the time per SCF drops from 164 around 150 seconds to like just half a minute, like 30 seconds. And to give why this is important is that now we are able to solve the full ground state for this system in just 30 minutes. And this is a very important problem for understanding the stability of quasi-crystals. I will talk about this towards the end. The next thing I want to discuss is our minimum wall time comparison with plane wave codes. So here we see that we take the BCC molybdenum system with increasing sizes, and we compare the minimum wall time against quantum espresso on the NARS Core CPU machine, and DFT-FE also on the NARS Core CPU machine. And we are getting almost 15x speed up in minimum wall time as we go to larger system sizes, and further when DFT-FE is run on GPUs, we get another 10x boost. And the full runtime of DFT-FE on systems of 400 and 1000 atoms we can do in about a minute and 2 minutes. So this runtime is including the full SCF convergence with initialization and forces. So this really shows that the strong parallel scaling of DFT-FE really enables this kind of, makes this large scale system sizes very routine. Previously, hundreds of atoms was the limit. Now, like thousands of atoms are becoming routine now with this. So one challenge which the community had missed in this focus on large scale and fast DFT, I mean, there have been works, but it has not received enough attention, is the SCF challenge in DFT. So when we go to large system sizes, the Kohn-Sham fixed point iteration becomes ill-conditioned, and I will discuss why. And also when we go to heterogeneous material systems with complicated dielectric functions, there is another source of ill-conditioning which appears. So now we'll talk about a preconditioning approach which alleviates these problems. So in the Kohn-Sham problem, we are trying to solve this fixed point iteration, f of rho minus rho equal to 0. We're driving this residual to 0. So if one uses a Newton step, one can actually get quadratic convergence, but unfortunately, we don't computing the explicit Jacobian inverse is very costly because this is the, if one were to compute the explicit Jacobian, it will scale n to the power 4 with number of electrons. And the Jacobian of this fixed point iteration is related to the actually the dielectric matrix of the system, where this dou f by dou v is actually the independent particle susceptibility matrix, and the dou v by dou rho is the kernel potential. So, so because there is a lack of computing this Jacobian explicit is expensive, what typically is performed is a preconditioned quasi-Newton step, where we take an approximate, the p operator, which is approximate to the Jacobian inverse, and we take an alpha, which is kind of between a damping parameter, which is between 0 to 1. And one can do some analysis to show that near the ground state solution, the necessary condition for convergence is essentially the spectral radius or the largest eigenvalue of this operator must be less than 1. And one can, in the linear regime near the ground state solution, one can show that that optimal alpha, which minimizes the spectral radius, gives to this following spectral radius. So basically what it shows is that even if you tune alpha, you are constrained by the condition number. So here k is the condition number, and so if you have a large condition number, essentially you have very slow convergence rate, because this, as the condition number increases, the spectral radius tends to 1. And the widely used preconditioning techniques in DFT codes are primarily multi-second methods like Anderson, Poulet, and we know some physical properties of the dielectric matrix. For example, in bulk metallic systems, the dou v by dou rho has the Coulomb potential, and in the Fourier space, in the long wavelength limit, it diverges. So using that notion, Kircher preconditioners have been developed, and also in the semiconducting systems, there have been Resta preconditioners, but so far there has not been a generic approach which works for a generic large-scale material systems. And also there is this problem of localized states like D and F orbitals, which have large density of states near the Fermi level, and that leads to large eigenvalues of the susceptibility matrix chi0. So all these are like sources of ill conditioning of the Jacobian. So the approach we are following is motivated from work by Niklason, where we take a low rank approximation of the Jacobian, which is composed of like this orthogonal direction functions ui, and the ti's are the directional response of the residual along those direction functions ui. And as I'll be showing, typically a rank of 5 to 10 is sufficient for the preconditioning purposes. And a good choice for the direction functions are the Krylov subspace of the Jacobian. And why that is a good choice? Because we are eventually interested in applying the Jacobian inverse to the residual. And as done in many linear solver approaches, that's why the Krylov subspace is a good approach. But we don't have knowledge of the true Jacobian. So how do we actually use the Krylov subspace approach? So we take the first direction function to the normalized residual and compute the directional response, so they get two derivative of the residual along the direction functions. Then we take the next direction function to be the previous response function, and we kind of keep orthogonalizing using Gram-Schmidt procedure those direction functions. So it is not a true Krylov subspace because we are orthogonalizing them, but it is close enough. And then once we construct this low rank form, we apply the Jacobian inverse using a pseudo inverse, where this low rank preconditioner is essentially the pseudo inverse of this low rank Jacobian. What we have done in this PRB submission recently, which got published, was that we extended this, applied this LRDM, this low rank preconditioning method to Kohn-Sham DFT, and have also extended to accumulated approach, where instead of throwing off this low rank form, so this is computed every SCF, so it can have some overhead. So instead of throwing off this low rank form, we reuse that in an adaptive approach, where the low rank from the previous SCFs is also reused, and we have a linearity indicator where we check based on the linearity indicator when to clear the accumulation and start afresh. And I've also extended this approach to spin polarized DFT. And another key advance from our side was that how do we compute this direction density response, the get-to derivative efficiently in conjunction with our Chebyshev filtered finite element procedure. And the approach is as follows. So if one were to compute this the get-to derivatives, the traditional approach is to use the density functional perturbation theory, but that is very costly because that involves computing the response, the first order response of each of the eigenfunctions, and that has to be solved on all the unoccupied states. So that can be very costly, and that's why typically these approaches were not used. But instead, what we do is we compute the responses in smaller subspace, and the subspace we have is actually the Chebyshev filtered eigen subspace. So we have the approximate eigenfunctions in the Chebyshev filtered eigen subspace. So we have the discrete Hamiltonian. We project our discrete Hamiltonian into the Chebyshev filtered approximate eigen subspace, so orthogonal projection. And then instead of taking so gamma is the density matrix, instead of taking f of h, which will be the full density matrix, and that will be very difficult to deal with, we work with the projected density matrix. And in fact, the Rayleigh-Ridge step, what I'm actually writing here is showing the Rayleigh-Ridge step. The Rayleigh-Ridge step in DFT-FE can be recast as this, where we are computing the diagonal of the projected density matrix, where we are projecting the Hamiltonian into the smaller subspace. And motivated from this, the response can be also computed in a cheap manner, where we hold this space onto which you're projecting the Hamiltonian to be fixed. We don't perturb it. We only perturb our Hamiltonian, and we project the perturbed Hamiltonian into this unperturbed subspace, and then we compute the response in that the response of the density matrix in that subspace, and this response has to be traceless because we have to fix the number of electrons should not change, and the traceless condition actually gives us the response in the Fermi energy as well. And then if you take the diagonal of the response, we end up with the response in the output density, which is what we want. And to compute this density matrix response, we use the canonical density matrix perturbation theory, which is developed by Nicolason. And in this approach, there is no additional diagonalization cost because diagonalization can be a large overhead. So this leads to a order n-cube method preconditioning approach with a small prefactor. And now I show some benchmarks of comparing this preconditioning approach against widely used preconditioning approaches for a range of system sizes. We're going from 100 atoms to 1,000 atoms, from almost close to 20,000 electrons, and we're solving all these benchmarks to a tight accuracy of 1e minus 5 in the L2 norm of the electron density residual, or equivalently close to 5e minus 8 in the total energy. And we are using Fermi Dirac smearing temperature 500 Kelvin, and this smearing temperature is actually reasonably small. Sometimes, many cases, actually material scientists use much higher smearing temperatures. But I feel better to use low temperatures because they will be more accurate to the 0 Kelvin limit. So what we see is that our preconditioning approach converges within 30 SCF iterations. And we are taking like large metallic nanoparticles, and we are taking insulating layers, semiconducting layers, and then metal semiconducting insulating layers like MIS, all the 3 heterogeneous systems. And also there is another system which is a hafnium oxide nanofilm with aluminum stripes. So as you can see, as we increase the complexity of the system, the condition number of the Jacobian significantly increases. But the number of SCFs do not increase. They are still within 30, whereas the rank does somewhat increase. It's weakly dependent on the condition number. Whereas the other preconditioners, they take 3 to 5x more SCF iterations. So I will compare against Anderson, which is a multi-second type, and Kirker is like, we know Kirker is good for bulk metallic systems, but as you can see, it doesn't do well for metallic nanoparticles. And TFW is a Thomas Fermi von Weizsäcker preconditioner, which is based on the kinetic energy functional approximation, because you can somehow pose the independent particle susceptibility matrix as the inverse of the double functional derivative of the TS of rho, the kinetic energy functional. So it is motivated from that, but since kinetic energy functional, we don't have a good approximation in terms of rho, it, as you can see, doesn't perform well for highly heterogeneous systems because the dielectric function is very complicated. And that is also reflective of the rank. So the rank we choose is not manual. We have an adaptive approach of choosing the rank. And this, again, I'm showing how total energy is converging. The green is our approach, and it nicely converges. And we have a spin polarized extension where we have the direction functions are taken to be now pair of spin up and spin down functions. And there is also the low rank approximation we construct now inherently has a spin-spin coupling as well in the response. Like essentially what I mean to say is that if I take a direction function in a spin up, it can have a response in the spin down and vice versa. So that coupling is automatically coming in. And as you can see, we're doing very well for spin polarized systems as well. And whereas this is a platinum bimetallic nickel nanoparticle, and some of the other approaches are taking a lot of SCF iterations. And this was a comment from a reviewer, can you apply it to a very low Fermi-Dirac smearing? We said, okay, why not? Okay, then we tried to 10 Kelvin, very low temperature, and there also we are performing well. And now the question is, okay, what is the computational cost of this approach? And we studied that also, and it has a very low overhead. In fact, we're getting a 3.4x computational saving in the total SCF iterations. We're using our approach versus the Kirker preconditioning approach. We choose Kirker because that was the best preconditioner in the more commonly used ones for these systems. And the per SCF overhead is around 1.5 to 2x. So it's a very practical approach. And now we do a little bit of advertisement. Here is a DFT-FE open source code, and we have a GitHub link. So far, we can do non-consuming pseudo potentials. We can do all electron calculations. We have density-based XC functionals, but we have ongoing work on developing accurate machine learned exchange correlation functionals, which are trained on exact exchange correlation potentials coming from inverse DFT. We can do ground state energy, geometry relaxation, MD, so the maximum sizes we have gone are 150,000 electrons in pseudo potentials and 10,000 electron in all electron. And recently we achieved almost 400 petaflops performance using almost 3/4 of the entire frontier machine on a 155K electron systems with 3K points at very good efficiency, 36%. So now I change gears to come to that initial motivation slide I had about ductility enhancement in magnesium alloys using solute. So what is the problem in, and here is really so what is the importance of putting in all this hard work of developing a large scale DFT code with this efficient preconditioning and system level convergence. So this example I hope will convince the audience that such capability is important. So what happens in magnesium is that, let's say we take this dislocation loop, which has a screw segment, and this is the edge segment. So in magnesium, the pyramidal edge dislocation is actually a higher energy compared to its transformed form in the basal dissociated edge. So the pyramidal edge is easy to glide, but the basal dissociated edge just get locked in, it's sessile. But because it's a lower energy, there is a small transformation barrier of 0.5 eV, which in a room temperature case, because thermal activation, it easily jumps, and that's what we observe. If you take a pure magnesium and look at TM, we mostly see basal dislocations and some basal locked pyramidal dislocations probably. That's why the non-basal slip is not getting activated. But there is a competing mechanism in magnesium. The competing mechanism is that there is a pyramidal screw segment, and the pyramidal-II screw can actually cross-slip to a higher energy pyramidal-I screw. So pyramidal-I screw has a slightly higher energy than pyramidal-II screw, but the energy barrier for this cross-slip is much higher. And because this bad detrimental transformation rate is much higher than the cross-slip, that's why we don't practically see the pyramidal systems getting activated. So one approach which was suggested by this science paper was that maybe using solutes we can enhance the cross-slip rate by reducing this cross-slip energy barrier. And that was the motivation, and they developed an analytical model based on, it's a phenomenological model based on line tension model, where the cross-slip barrier is modeled as follows, where you have so I'll get deeper into this model, but the main motivation here is that the cross-slip barrier is very sensitive to this core energy difference between the pyramidal 1 and 2 screw dislocations. And in their model, they were using this value from MEM potentials, but they commented that it was very, very sensitive and a slight. So ideally, they want to get this energy difference to under 5 MeV per nanometer, and using large-scale DFT calculations, which has not been possible yet. And that's what I'll show in the subsequent slide. This is possible through our approaches. And further, this energy difference can be tuned by solute additions. And so both the pure energy, core energy difference, and how this energy difference get modified by dislocation-solute interaction, all these quantities are critical in predicting this energy, the cross-slip barrier through this line tension model. So what we did was, we did a systematic cell size study of the core energy difference between the pyramidal 2 and the pyramidal 1 dislocation. And these studies were using very fine discretization. In fact, we found that like if you are like around 1 millihatri per atom, the energies were, the energy difference was very sensitive. We really had to go to under 0.1 millihatri per atom in the energy, and also the force error was also very critical, and we had to really go under 0.1 millihatri per po in the forces, and we had to use like a lot of K points along the dislocation line. So we went from like this is I'm showing the number of atoms in the periodic layer. We systematically went from 800 atoms to almost like 3000 atoms per periodic layer, which is close to 30,000 electrons. We're using 10 valence electrons per atom, which is a accurate magnesium pseudopotential. And we see that really have to go beyond close to that 3000 atoms per periodic layer to get the convergence in the energy difference between the two dislocations. And further, we find that this energy difference is sensitive to externally applied macroscopic strain in the non-glide strains. For example, if we apply uniaxial strain in the 3 directions, we see that the slope of the dependence of the core energy difference with respect to the macroscopic strain is non-zero. And I will soon demonstrate why. Demonstrate why this getting such a high accuracy is practically important, and also why this new physics, which was not modeled yet, that is also important to include in the cross-slip model. So before I demonstrate the results on the cross-slip model, I would like to spend some time discussing how this model is constructed. So, so in the cross-slip energy barrier model, with the first term is essentially the intrinsic barrier, because to nucleate the cross-slip going from pyramidal 2 to pyramidal 1, you have to nucleate a initial segment, which is like a jog step, and that nucleation barrier we are taking from MEM potential. And then there is as the cross-slip length expands, so this cross-slip barrier modeling as a function of L, as the cross-slip length expands, so this is this L. There is a energy penalty because the pyramidal 1 has a higher energy, so that's the energy penalty term. And further, because you are applying, there is a resolved shear stress, tau. which is acting on the delta tau, which is acting on the pyramidal 1 plane, so which bows out the dislocation line after it jumps to the pyramidal 1 plane, and that bowing out increases the segment length. So there is an energy penalty corresponding to that, which is the dislocation line tension multiplied by the change in the segment length. And then there is also work done, negative work done, because it is externally applied resolved shear stress, and this is multiplied by the area swept by the pyramidal, the dislocation bowing out. And these quantities are just obtained from geometry and as well as the equilibrium condition of the line tension and the peach color force acting on the pyramidal 1 dislocation. And what we're interested is getting the where this barrier is maximized. So I just showing a more like a numerical figure. As we increase the cross slip length, we reach this maxima here. So essentially, once we a thermal activation is provided, where we reach this critical cross slip length, the cross slip just happens unboundedly. So we are interested in what is this maxima, and that is our essentially our critical, that gives us the critical nucleation length for cross slip and our expected barrier. And what I did not mention here is that, okay, how do we get this delta tau? Because that is also related to our, that is related to the Piles barrier on the pyramidal 2 and 1 planes, as well as the SMID factors. So this is to motivate that, I take this schematic. So we have the 3 axes. So the x1 is along the A axis, and the x3 is along the C axis, and x2 is along the C cross A axis. And we have a loading, we are applying a tensile loading where sigma direction in this direction, which makes an angle phi with the x3, and also the projection of this direction on the basal plane makes an angle psi with the x1. So this is more representative of the textures we get in this magnesium alloys, which are typically, if you are using a pure magnesium, you get a basal oriented texture. But if you are having a like a magnesium alloy with rare earth solute, you get something called a DPRD texture, where the this vector makes an angle like a phi, which is like 75 degrees with the C axis. So it is, or you can say that the vector is making an angle 15 degrees with the projection on the basal plane. So it's slightly offset from the basal plane. And then we are studying the quasi-static loading condition, which means that we first write the resolved shear stress on the pyramidal 2 and the resolved shear stress on the pyramidal 1. These are just SMID factors. And the equilibrium condition is that the resolved shear stress on the pyramidal 2 matches the Piles barrier in the pyramidal 2, which gives us this sigma. And then using that, we compute what is the net resolved shear stress acting on pyramidal 1, which drives the cross slip process. And based on numerical averaging over psi, we get this following estimate. And in these calculations, we are using the single crystal Piles barrier for pure magnesium, which are 42 megapascals and 50 megapascals for the pyramidal 2 and pyramidal 1 respectively. And here are the predictions of our cross slip barriers. Using the MEM delta E, we get a 2.5 EV prediction. And using the DFT result from this work, which are 16 MeV per nanometer, so the difference is not much, just 10 MeV per nanometer, but the cross slip barrier significantly dropped and changed. And that is really because there is a magnification factor, like because this nucleation length can be very large. So even a small change in your energy difference can get magnified in the prediction of the cross slip barrier. And also we find that once we account for the macroscopic strain dependence on the core energy difference, the barrier further drops to 0.7 eV. So this shows that there has been a missing physics as well, and also the large scale DFT calculations at low discretization errors is very important to correctly quantitatively model these barriers. And next I talk about because this model is still not complete. We have only talked about pure magnesium, but what we really care about is, can we predict, quantitatively predict the increased ductility of magnesium yttrium alloys at low concentrations, which means that what we are really trying to predict is this delta Gxs as a function of the concentration of yttrium, and that we're hoping that we were able to model that it sharply drops at small concentrations. So for that we compute the dislocation-solute binding energies, and we take some near core sites from common neighbor analysis, and because the what we're interested is in the difference of the dislocation-solute binding energies. So at far field, the pyramidal 1 and the pyramidal 2 screw dislocations, their far field elastic fields are the same because they have the same Burgers vector and the line direction. So we have to take a subset of sites. We don't have to take so many sites. So we take this green colored sites, disordered sites, and a layer around it, which is around 60 sites. In fact, we have also gone to more sites, and we find that our eventual predictions don't change. So and we compute the dislocation-solute interaction energy for each site by taking a substitution solute near the core and another one far away from the core and subtracting them out. What we find is that, in fact, for this kind of getting the convergence in the dislocation-solute energy, you have to go to even larger system sizes. And the reason for that is when you put a solute in a computational domain, and we are using periodic boundary conditions along the normal to the plane of the paper, you can have solute-solute interactions. So you have to also converge with respect to that. So we find that almost a 4 Burgers periodic layer, which is close to 2.4 nanometer, is required to remove those spurious effects. And then we also compute the difference in the interaction energy between the pyramidal 1 and pyramidal 2. So here are the maps, and this is for the pyramidal 1, the binding energy map, and this is for the pyramidal 2. And those sites are, so I'm showing here the core, not the relaxed core structure. I'm mapping it back to the original lattice so that it is easier for visualization. And this is the difference of the dislocation-solute interaction energies. What we really care about is this one. I mean, as far as the initial model goes, but I'll show you subsequently that these things also matter. So what we see is that once you put in the dislocation-solute interaction, there is an average effect and there is a fluctuation effect. So the average effect comes out because every site has a probability of occupation, which is the concentration of the solute. I'm probably running out of time. I'll go faster. And there's a fluctuation effect because it's coming from the random occupancy of the solute. And we use our explicit dislocation-solute data to compute this both average and fluctuation effects. And we compared that also to the previous approach. In the previous approach, using this work, they're using the stacking for solute interaction as a proxy instead of explicitly computing the dislocation-solute interaction. So we find that the predictions are vastly different. In fact, we're getting highly negative binding energy on average, and they're getting highly negative, we are getting highly positive. So we are predicting that actually the pyramidal 1 screw dislocation would not become stable for using yttrium, and that leads to, when we plot the cross-slip barrier with yttrium concentration, we see that the barrier just increases. So what this means is that we are not able to predict the increased cross-slip activity in dilute magnesium alloys using this model. So there is something missing in the model, and this is also evident from looking at the this experimental data. We shows that at higher concentration of yttrium, the pyramidal 1 dislocations, which is the first order pyramidal plane, that is more visible. That is observed, but not the second order pyramidal slip is not actually observed at higher yttrium concentration. So previously the thinking in the community was that, okay, because we had this negative energy binding energy difference, that was driving the pyramidal 1 to be more stable. But what we find is that is not the case. In fact, the energy of pyramidal 1 keeps on increasing. So what are we missing here? So then we thought about, okay, like maybe we are missing the solute strengthening effect, because when you have a random dislocation in a random environment of solutes, it attains a wavy texture, and the waviness can be characterized by this Labouche type solute strengthening model. And then to characterize this waviness, so what happens is that the dislocation line, it becomes wavy because it tries to avail this favorable solute fluctuations. So it tries to kind of glide, so this is a slip plane, and it glides a little bit along these slip planes to avail these favorable configurations and reduces the its energy. So there is an increase in the energy because it's bowing out, but there is a decrease in the energy because of the favorable solute fluctuation. So overall, it leads to kind of like a sinusoidal landscape where the depth of the well is given by this standard deviations of this solute fluctuations. And I won't go into detail of this. So this is very well established theory, but finally we get this prediction of the additional strengthening in the yield stress, which is dependent on the solute concentration, and it scales as c to the power 2 by 3. And after applying this to the pyramidal dislocations, what we find is that interestingly find that the pyramidal 2 screw strengthening, the critical resolve stress drastically increases at higher concentrations of yttrium, whereas the pyramidal 1 screw, it slowly increases, and that also corresponds to the experimental observations, because what this shows is that at a higher concentration of yttrium, the activity of the pyramidal 1 should be more because it has a lower critical resolution, and that's what we are seeing from the experiments. And also beyond a certain yttrium concentration, it becomes higher than the experimental prismatic slip, and that's why at very high concentrations we only see prismatic slip. And then we introduce this the critical results, critical results dependency on the solutes we introduce into a model. So this is a final model which has all the field. It has the macroscopic dependence of the core energy. It has the average interaction effect of the solutes. It has this fluctuation interaction, and this is now the net result shear stress is also modified by the solutes, and this is what we see in the Crossley barrier. If you don't, initially the barrier was just increasing, but now if we introduce this solute strengthening coming from the Labus model, the barrier nicely reduces now for increasing concentration of yttrium, and further if we introduce the delta E dependency on the macroscopic strain, the barrier further reduces. So it shows that incorporating all these effects is very important. And but one thing I want to point out is that, okay, this is the barrier, but the actual reaction rate has this dependency with the critical nucleation length, because if you have the critical nucleation length is very large, as you can see the nucleation length changes with concentration, it will reduce your atoms, and whereas the critical nucleation length for the pyramidal to basal transition is just 2 nanometer, so it can have more atoms. So we kind of also study the logarithmic change of the difference between the total rate of the this is the cross slip rate and the total rate of the pyramidal basal transition. And when we compare that, we see that this chi, which is the factor chi, so more than 1 means the cross slip rate is more than 10 times compared to the pyramidal basal transition. So we are able to see that beyond 0.1 yttrium concentration, we are getting the cross slip rate to be very high compared to the pyramidal basal transition, and which also matches with experiments. So this is at 0.3 atomic percent yttrium, and we are seeing that high ductility in those regimes. And this is the tensile stress of which we get from model at different yttrium concentrations. One has to be a little bit careful about the applicability zone of this model. So I will, running out of time, this is a quasi-crystal simulation we did, and that's, yeah, thank you. Yeah.